Now we will learn about integration. What we have learned till now, first we learned about limits, then we learned about slopes. And slopes were obtained by taking the slope of a secant line, and then taking the limit of that as the 2 points come close to each other. And that's why we had learned about limits, and that gave us the definition of a derivative. And then we learned a lot of techniques and rules about how to find derivatives of different functions. And then we said the opposite of derivation process, taking a derivative, was the antiderivative or the indefinite integral. Now we'll start learning about something called integration, which will have something to do with finding the area of a function under the curve. And then, amazingly, we will see how this is connected to the antiderivative and the indefinite integral that we have learned about. Okay, so to first start about integration, we will start learning about the sigma summation notation. Okay, you might have learned that before, or maybe not, to calculate sums and powers of integers. And then we will use that to understand the approximation of an area under a curve. And then something specific called Riemann sums to approximate area. Okay, so the first thing, sigma notation. So here, when you're trying to add all these numbers, we can represent that as summation sign, which is this sign over here, summation sign of I, where I goes from 1 to 20. So what specifically it means is, take I first to be 1, then add to it, and now take I to be 2, then add to it I 3, and you keep doing it till you reach the top value. So you start with the bottom value, reach the top value. So summation of I equals 1 to 20 means replace I with 1 here in this formula and add to it 2, 3 up to 20. Similarly, in a sigma notation, we can say sum, not I, but AI, something that's a function of I, where you put I equals 1 first, so A1, then replace it with 2, 3, and add up to AN. So that is the meaning of this notation. Okay, so here's an example. Write in sigma notation and evaluate the sum of 3 over I, where I goes from 1 to 3, 4, 5. So we'll show it as 3 to the I, we are adding, some, where I goes from 1 to 5. So take in this formula, first I equals 1, it becomes 3 to the 1, and which is 3, then plus, add 3 where you replace I with 2, then 3, then 4, then 5. So this is the meaning of this summation notation. Okay, what about this one? So this one would be, first take I to be 1, so 1 over 1 square, plus then replace I with 2, so 1 over 2 square, plus 1 over 3 square, 1 over 4 square, up to the top value, 1 over 5 square. Okay, now the sigma notation, we will see if you add a constant n times, which means, see, c is not a function of I, so first time you add c. Second time you again add c, and you keep adding n times. If it is n times, so it becomes nc. On the other hand, if you have cai, the summation sign goes through c. So summation, just like derivatives and the antiderivative, is a linear function. So c comes out, so you can see like ca1 plus ca2 plus ca3 up to can is same thing as take c out and add a1 up to an. So this is shown as summation of cai, I goes from 1 to n, and this one is shown as c, summation ai, I goes from 1 to n. And these two obviously are the same. So the summation sign goes through the c. All right? Then similarly, if you have summation of ai plus bi, the summation sign just goes through linearly to each of the terms. Same with minus. Okay, and we can prove that easily. And if you're doing the summation from 1 to n, you can first do it from 1 to m and then m plus 1 to n. So if you're adding a1, a2 up to a5, you can add, for example, a1 plus a2 plus a3 in one, then a4 plus a5 in the other. Pretty straightforward and simple. Now, 3 formulas which we can prove by induction, that if you add the first n numbers, the formula for that is given by n plus 1 over 2. So for example, if you add 1 plus 2 plus 3 plus up to 100, this will be equal to 100 times 101 over 2. And one easy way to show it is take s to be 1 plus 2 plus 3 up to n. S can also be written as, if you write all these terms in a flipped way, we can write n plus n minus 1 plus n minus 2 plus 2, 3, 2, 1 plus 1. So if you add now each of these terms together, so if you add these two, we get 2s equals, we get n plus 1, how many times? N times. And therefore the sum equals n times n plus 1 over 2, which is the proof here. Okay, similarly we can prove that if you add the squares of the first n terms, the formula is given by n times n plus 1, similar to this, times 2n plus 1 over 6. And if you add the cubes of n terms, it is just the square of this, square of that. N plus 1 over 2 whole squared. Okay, so let's see some of the terms I minus 3 squared from 1 to 200. If you have to do this. And then similarly, this one. So step number 1, you expand your quadratic expression. You get this. And remember then summation is a linear one. It goes through here, so we get I squared. Then 6i, but 6 comes out, so we get this one. And this is just a constant. So we use the formula for I squared when you add 1 to n, which is n plus 1 times 2n plus 1 over 6. You get this one. This one is 6 times, we are adding n plus 1 over 2. We just did those formula. And here we adding constant 9. How many times? 200 times. So times 200. We get this answer. Now next one, you just apply the formula for summing I cubed ones, which is n plus 1 over 2 whole squared, where n is 6. And then I squared is n plus 1 times 2n plus 1 over 6. Add these and we get the sums. Similarly, if you want to add x cubed from 1 to 10, like this, just apply the formula n plus 1 over 2 whole squared. So n squared plus n plus 1 squared over 2 squared, where n is 10. Okay. Now we will see that if you want to approximate the area of a function, we can get a summation for that. How? Okay, so first we will divide the interval a to b into n subintervals of equal width b minus a over n. So this is 1, 2, 3, 4, 5, 6, 7, and then 8th last one, for example, or 9 and 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this will be equal lengths, of course, you know, it doesn't look like it here. So then the width of each one will be b minus a over n. So we get x0 up to xn, where x0 is a, and then xn is b. This one is b. So this would be x0, and we have x10 over here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So these are the points we get by dividing the interval into equal number of points. And then to approximate the area. So first of all, we have now these subintervals, and they are called the partition of the interval AB. And if we divide it into equal intervals, same width, we call it a regular partition of the interval a to b. So we can approximate the area many different ways. One way is to take left-hand approximation. So you take for example, we have x0, x1, x2, x3, up to xn, right? So we have done the partition. The first one, you take the function value to be fx0 times delta x, which is the width. And remember, what is the width? Delta x is b minus a over n. So this function value times this width is this rectangular area. Then you come to the next point and take the function value and approximate this one. So of course, this is not the actual area from here to here. See, we are missing these, but it is an approximation. So this is the approximate area using left-hand approximation of the function on these regular intervals. We could also approximate using right-hand approximations. So for example, the first one would not be based on taking this point, but taking the last point. So they both are approximations. In general, they'll have different values, but they'll be both close to the area in general. Okay? So depending on how many points you take for the function. So this is the left-hand approximation or the right-hand approximation. So for example, if you divide and you have n points, okay, so x0 to x6, and we are taking the left-hand approximation, the area would be, if you put fx0 times 0.5. For example, in this case, we have divided into 6, and the whole interval is 3. So 3 minus 0 over 6, each value is 0.5. So 1, 2, 3, 4, 5, and 6. So the points we have is x0, x1, x2, x3, x4, x5, and x6. So you take f of 0 times 0.5, f of 0.5 times 0.5, and so on. So depending on whatever the function is. So for example, if the function is x squared over 2, f of 0 is 0. What is f of 0.5? Which is 0.5 squared over 2. That will be 0.125. What is f1? 1 squared over 2, which is 0.5. And so on. So you find if you want the approximate area of the function from 0 to 3, okay, you divide it into some n intervals. In this case, we have divided into 6 intervals. So the width of each one is 6 minus 0, 3 minus 0, because the interval is 0 to 3. And we have divided n is equal to 6. So delta x is equal to 0.5. And the values we're taking, the left-hand approximation, left side approximation, is given by this number. On the other hand, this one is the right-hand approximation. So in this case, you start with f of 0.5 times 0.5. That's the first one. So this is 0, 0.5. So first area is given by f of 0.5 times 0.5. In here, the first one is given by f of 0 times 0.5, because you're taking the left points for each one. Here you're taking the right one. Right one is f of 0.5 times 0.5. So here the approximations are fx1, fx2, fx3 up to fx6. These are the ones we're adding. So this is the right-hand approximation. The left-hand approximation goes from fx0 to fx5. So in general, they won't be same, but close to each other. And to find the actual area, what we do is we'll divide the interval. Instead of 6, we'll take maybe 10, then 20, 100. So we'll get different approximations. These different approximations when we get, if we get limit of these values, as you make infinitely many intervals, that limit, if that sequence has a limit, we call that limit the area of the function under this curve from A to B. Okay, so So here's an example. Fx is given as x squared. We have an interval 0, 2. And we're dividing n into 4 parts. Okay, and use both left and right endpoint approximations. Okay, so delta x will be 2 minus 0 over 4, which is 0.5 once again. N is 4. So the left-hand approximation, L4, 4 means how many intervals we are taking, fx0 delta x, fx1, fx2, fx3. And since the delta x is 0.5, so we have the function at 0, at 0.5, 1, 1.5, 1, 2, 3, 4. So the left-hand value will be f of 0, which is 0, f of 0.5, the function is x squared. So f of 1 goes here, f of 1.5, and so we're doing the left hand, f of 0, f of 0.5, f of 1.0, 0.0, 0.5, 1, and 1.5. These are the 4 values of the functions we get, f0, f.5, f1, and f1.5. And you multiply each one with delta x. So this is the left-hand approximation of the area. Just plug in the values and you get 1.75. On the other hand, if you want to do the right-hand approximation, you'll take this value for this area, this value for this area, this one here, and this one here. So instead of f0, 0.51 and 1.5, we'll take f1 delta x plus f2 delta x plus f3, these are x1, x2, x3, and x4. So not x0. So 1, the first point will be 0.5, 1, 1.5 delta x plus f of 2 delta x as compared to f of 0, f of 0.5, f of 1, and f of 1.5. So instead of this one, we add f2 here. So these are the 4 you take for the right-hand approximation of the area. And here it is. F of x1, x2, x3, and x4. As compared to f of 0, x0, f of x1, f of x2, and f of x3. Okay, and we can improve the approximations by taking the interval and having more partition points. So as we increase the partition points, you will see that our approximation of the area will get better and better. And if in the limit as n goes to infinity, the number we get, we define it to be the area of the function under the curve. Okay, so now the Riemann sums, forming Riemann sums. Riemann sums means in each interval, instead of taking a left and a right, arbitrarily take some point, x star, within each interval. Okay, so instead of taking the left-hand point or the right-hand point, divide the the whole interval a to b into subintervals. So partition it, and then in each interval, just take a point, any point, and use that to approximate the area. That height times delta x. Next one. So fx1 star in the first interval, and fx2 star, and so on. And that is called the Riemann sum. Okay, and that approximates the area, and then the area is defined as if you take the partition in the limit n goes to infinity. And this is that's why we learned the summation sign. So we are adding fx1 star delta x plus fx2 star delta x, and we are adding up to fxn star delta x. We're adding n of these. And then we're taking a limit of that as n goes to infinity. So if you take n equals 10, divide it into 10 intervals, take points in each interval, approximate, write the number. Then do it again when n is bigger, maybe 20 intervals, subintervals. N is 50, 100, 1,000. So as n keeps increasing, your approximation will get better and better. And in the limit, if you get an answer. So this process is similar to how we define the derivative of a function. We took a point at one point, x, and then a plus h, x plus h. And then we took another one, as h went to 0, the limit was the slope. So here we're taking an interval and we're taking n intervals and finding approximated area. Then we're increasing the value of n. Then again increasing, and we get different approximations. As n goes to infinity, the limit we call the area under the curve. Okay, another example. We are given the function, this one. Okay, find a lower sum again. So 1 to 2. So what is delta x? 2 minus 1 over 4. So delta x is 1 again, once again 1 over 4. And the intervals from 1 to 2 is 1 to 1.25, because 1 over 4 is 0.25. 1.25 to 1.5, 1.5 to 1.75, 1.75 to 2. And then the L for the left side will use f of 0 delta x plus f of 1 delta x plus f of, so left ones, oh, not 0, 1, 1.25. So these intervals, left, 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 and left. So left points, if you take the left points, we get f of 1 delta x plus f of 1.25 delta x plus f of 1.5 delta x plus f of 1.75 delta x. And we can easily find these function values by plugging in into x1, for example here, that would give us 10 minus 1 is 9 times 1 over 4 or 0.25, and so on. And for the right one, right 4, we take these values, right-hand interval values. So f of 1.25 delta x plus f of 1.5 delta x plus f of 1.75 delta x plus f of 2 delta x. And you can see the difference between these two is in the right hand one, this one is not there, and we are adding this last one onto here. Okay, and the rest is just computation. We can easily compute this one using a calculator or a computer. Okay, so here it is. So they have taken 0.25 outside the summation and then added the function values. Okay, for left, and you can also do it for right approximations. Okay, you can do the same thing for sine x. So each one of these is very similar now.